Cool. So, hi everybody. Thanks to everyone for coming. We are here to talk about how to get the absolute most out of PyPy. So I think first we're going to start off introducing ourselves. I'm Alex Gaynor. I've been working on PyPy for probably about 2.5 years now, and I've been working on just about every part of it, the JIT, the Python interpreter, and we're going to talk about more about what all these levels are and why they exist. So, Maciek, do you want to?
I'm Maciej Fiałkowski, and I also work on pretty much everything since 2006 or so. And we're gonna probably run something like talk about 40 to 45 minutes, and the questions and stuff should be as interactive as possible. And like ask questions anytime you want. And then we'll run like hands-on, we'll give you some code to try and optimize and see how it goes. And Armin, would you like to introduce yourself?
Yes, I'm Amir Rigaud, and I work on PyPy since beginning, which is 2003.
Right. So the first question we want to talk about is if we're here to talk about how to get the absolute most out of PyPy in terms of performance. How do I, next slide. Okay. So we got to ask what is optimization? So does anybody have any ideas about what might be the very first rule of optimization? No reading the gray text. Exactly. Optimization is the process of taking a program and changing it so that it has the same behavior, but it executes faster. If you've changed the behavior, then nothing else you've done matter. I can write a Fibonacci function that executes in 0 time, except for it's totally wrong because its implementation is return 1. This is not valid. So from the PyPy project's perspective, we are very big test-driven development enthusiasts because this is a way to have an automated way to tell when does your optimization work. Because, you know, working does not just mean faster. It means working. So the second rule of optimization, any guesses? No reading. Second rule of optimization is it must actually be faster. The purpose of your process is to make your code run faster. And that means that you need to have an automated way to know if it's faster. That means good reproducible benchmarks. In the same way you have tests of behavior, you need tests of performance. So you just need repeatability is the name of the game. Being able to have what you do always work and always work. Any guesses on the third and final rule? No one? Okay. Measure twice, cut once. It's really easy to take a small program and maybe tell why it's slow. You know, maybe it's 100 lines in a single file. It's easy to guess at. Large applications, you can't just guess why it's slow. You need to analyze and look at your benchmarks and try to understand what it is about them. So that means tooling in order to understand why things are fast and why things are slow. So these are sort of the rules of the game in terms of how you actually go about making code faster. You have a way to verify their behavior is correct, you have a way to verify when they get faster, and you have a way to verify what it is that's causing your slowdown so that you can work on that as your first priority. So people here, I'm guessing, are mostly interested in performance of things. So if people are probably mostly targeted CPython before in the past. What are some things you do on CPython to make your code run faster? Yeah. Okay. Oh. Okay, so C extensions are a big way to make things run fast on CPython. Anyone else? Any other guesses? Any sort of hacks or tricks you can think of? Bound methods is another big one. So we've come up with a short list of our own tricks that we found. So using map instead of list comprehensions. This is sort of the principle he was talking about, writing C code to do it. Map's inner loop is written in C, so on CPython that tends to be faster. Anytime you can find a function which has a loop for you, that tends to be a performance trick on CPython. Making globals local, so instead of doing in the middle of a loop looking up a global name, if you could somehow look it up earlier, that's faster. The bound method thing Dave talked about, grabbing the bound method that's loop. Function calls are slow. And most importantly, the less lines of Python you execute on CPython, the faster you tend to be. The more you can find a way to push your computations into C code, the faster they will be. These tricks are completely and utterly invalid. Ignore everything you thought you knew about writing fast code for Python when you're targeting PyPy. Dave? It, yeah. Yeah, so tricks sometimes work and sometimes don't. So we want to have a holistic understanding of what the performance characteristics of running Python code on PyPy are. What's fast, what's slow, what do we know about how stuff works. And I think the most important thing about optimizing for PyPy is operations don't exist in isolation. You can't say what is the speed of a function call. With all of PyPy's infrastructure, the speed of a function call matters. Is this function inlined by the just-in-time compiler? Are you calling a C function versus a Python function? Does the function have its own loop inside of it? All these sort of details we're going to be looking at. Operations do not exist alone. The canonical example of why can't you make Python fast is you have the function def f, which takes parameters x and y and returns x plus y. In isolation, we know, in theory, you have to do all these lookups. You have to look for the under add method on x, the under radd method on y, all these things. In the full context of what you're doing, the JIT can often see, oh, this f of x, y function really only ever takes integers. And so it has a different performance characteristics when it's known to be only working on integers. So operations do not exist on their own. So if you're all taking this tutorial, we've probably already convinced you it's worth knowing more about PyPy and maybe targeting it. But in general, there's 3 reasons to target PyPy, we think. Performance, memory, and our sandbox. We're really not going to be talking much about the sandbox today, other than it is a thing that lets you execute untrusted Python code without risk, really. But performance and memory are our real focuses for today. So this sort of the flip side is, why not PyPy? Embedding Python in some other like C application. We don't really have the APIs CPython has for this. Embedded platforms, like really low memory stuff, like single chip system. I don't know what you call them. Chip on a board. There's a term for them. Really tiny platforms. Things that aren't x86 or x86-64. We're working on ARM and PowerPC. So PowerPC apparently made some accomplishment today. It will be within, I don't know, a year. Both of those platforms will probably be ready.
We did a build, but stuff ordered.
Okay. So yes, if you have a machine you want to turn into a build bot, talk to us afterwards. So really, right now, what we have today, x86 on OS X, Windows 32, Linux 32 and 64 are our primary targeted platforms. If you're not targeting one of those, that's unfortunate. And the final thing is, if your code base is primarily or has very important C extensions, our support for CPython C API is not great. That does not mean we can't interface with C code, as we'll, again, talk about later. We have the ability to interface with C code, not C code that targets CPython's API, and that's the distinction we'll be hitting on. So the absolute main thing in terms of PyPy's performance is we have an interpreter and we have a JIT. CPython has just an interpreter. If you're familiar with like Chrome's V8, that's just a JIT. We have both, and that's pretty important. And this works by compiling PyPy to assembler via magic, which will hopefully be magicking after the day goes on. And this produces the very different performance characteristics. The important thing, and really the goal of what we're going to talk about today, is every virtual machine, every compiler, every interpreter, they have a sweet spot. That is operations whose performance they are optimal at. So sort of at its most basic level, most C code is within a good C compiler's hotspot. C is sufficiently low level that every operation is as efficient as maybe you'd expect it to be, or as an equivalently written thing by hand in machine code would be. It's a little hand wavy. We know it's possible to beat the compiler sometimes, but all C code is sort of efficient, and not all Python code is efficient. We have all these abstractions. We have the garbage collector. Everything is an object. We don't know the typeset. We have all these abstractions, which a lot of times we can defeat them, and we'll be talking about when we sort of, quote, defeat the abstraction and get the performance that, you know, we might expect that the raw machine has. But sometimes we don't, and understanding what that sweet spot is, what that set of operations that's as efficient as we'd like is the goal. And of course, we're always trying to expand the sweet spot. There are things that we say are inefficient today that might be more efficient tomorrow. It's unlikely that there are things that are efficient today that will be inefficient tomorrow. We have benchmarks and, you know, tests of our performance to try to ensure we never have regressions like that. So CPython's sweet spot really tends to be moving computation to C. So this is sort of an example of the tricks. So instead of doing x.a for x in mylist, we're moving into the attr getter and the mylist. And this is basically, CPython is just an interpreter. Every single function you have gets compiled to bytecode, which the CPython VM then executes. Virtual machines, interpreters like this, they have an overhead. Every single bytecode you execute, the interpreter needs to fetch the bytecode from memory, needs to decode what the operation is, needs to jump to its implementation of this. All of this has an overhead. I think we found that in PyPy, just removing that and doing absolutely nothing else is like a factor of 2 difference. Just removing the bytecode interpreter. Depends, but yeah. Depends, like everything. So PyPy's sweet spot is, you know, quote unquote, simple Pythons. Things which basically means if a human can read this and understand it, it tends to be that the machine can read it and understand it well, or not read it, but can execute and understand what it's doing. And in general, if the machine doesn't understand what it's doing, that's when you tend to leave the performance sweet spot. If it's somehow more complicated, it's not necessarily with the set of operations you do, but whether the JIT can see the full scope of what you're trying to do. That is, the more clearly you express your intentions to the JIT, the better it tends to be able to actually execute your intentions efficiently. So, you want to? Yes. Go.
Boom. Okay, so maybe the short introduction to the architecture. The architecture of PyPy is pretty confusing and people get constantly confused, but I'll try to keep that simple. So first, it's like bytecode interpreter. The bytecode interpreter itself is written in a high-level language. It doesn't quite matter what sort of high-level language this is, but this is not C. In our case, this is RPython, which happens to be a restricted subset of Python, but this is not that crucial. The crucial part is we have a description of the interpreter written in high-level language. And that gives us quite some possibilities that are relatively hard on CPython or any sort of VM that's written in C, because we are able to analyze the entire interpreter for things. So the main interpreter loop is written in RPython, and you can run PyPy as a Python program. So if you have a checkout, the checkout is on the USB sticks, or you can just check out it's from HG. You can just run in bin directory, there is py.py. You can run it. Well, I suggest you actually do. If you run py.py, it's a Python program that starts for like 20 seconds or something like this. It's really slow. But PyPy is a Python program that happens to interpret Python. It's specifically written, yes, but it's also a Python program that interprets Python. So if you run this and say a equals 3, for example, you can press Ctrl+C, and that will get you to a different level console where you get wrapped objects. So you'll have w_a that will be a wrapped object, that will be a Python object, but a Python object on the actual VM. not on the interpreter, Python interpreter.
This is usually where people get confused.
So we also wrote a JIT in our Python, and the important part is the JIT is an R Python. It's not a program really, it's a transformation. So we take our interpreter and we transform it to create a JIT for a Python interpreter. So for example, the way we test the JIT is we have tons of small R Python programs that happen to be very strange interpreters that test like various cases. We almost never test the JIT by running the full Python and then testing the JIT like you would do pretty much with everything else. We test like small pieces of our Python programs that are interpreters that we translate or like interpret or do something, and then we have a Python interpreter as well written as an R Python program. And assembler backend is a pretty typical thing. Like everybody else does this. You can. The thing is like we get constantly asked, why don't you just use LLVM? It solves the JIT issue. So the LLVM would solve this part. It wouldn't solve this part. And this is pretty crucial. LLVM is a assembler backend that can be reused for various architectures. Yes, it's quite a bit of work, but it's not a JIT as we need it for Python. So yes, well, I can show you. Well, if I try to like put on the slide what add opcode actually does in Python, it doesn't fit on one slide. We tried, I think, at some point. So I can show you, for example, can you swap the mics?
You want this one?
Yes. So I can type. Does it work? Yes. Okay. So I can show you, for example. Ooh, hello. I have a simple program. Yes, I know. Up. Yes, like this. Like this. No worries. Up. Up. Okay. So this is a Python program that's relatively boring. It like takes has a function that sums all the integers from 1 to some large number that I typed by chance. What it does, it will run the function, but first we'll drop the. So if I drop the Python bytecode, if I run it, maybe I should. Up. Up. So, ooh. Up. Okay, we can see. So if you run the example, it like will display the bytecode, and the bytecode is setup loop. Then you load the global X range, and then you load the constant, and then you call the function which will pick up variable and then a global which is X range. Then we'll have a loop, and loop starts here at for iter. It stores a variable I, loads the variable s, loads 1, adds stuff in place, stores and jumps back to here. So if we look back, this is just those 2 lines and not even full because it doesn't contain the construction of X range. I have like a special thingy that will display me what PyPy actually does, and then this is the display. So this is the source code. We have the X range, and those are Python bytecodes, and those are operations that happen, but those are operations that happen in the assembler. So I here is some variable, I don't know quite what, but a variable that's on the register usually. Like if we make this slightly smaller, we can show the assembler. So we'll see that, for example, I here would be in R10. So that's a register, that's C-level variable. So think about this as C code, except it's written in an obscure style. So then you do things, and this guard means guard that variable stays true. This is probably a loop condition. And then that's stuff, and among stuff, there's not that much assembler actually. So this will be, what's that? This is the counter that counts like current and remaining in X-range iterator. This is the addition that checks for overflow. So for example, if we overflow into longs, then this guard will fail and will resume in the interpreter. So this is like a single piece of assembler code. And this is just obscure. This is checking for Control-C working, essentially. So if you press Control-C, you actually get interrupted with like a correct position in the code. Up. Slides. So you execute bytecode and you do things. Then you get the loop that gets hot, and after about 1039 runs or 1619 function calls, you start tracing the function or a loop and generate operations as interpreter would execute them. Anyone can guess why it's 1039 and not 1000? So 1039 is a prime number. That's why. It's like first prime number above 1000, I think. And that's because, well, obscure reasons, but most importantly, if we have a tracer, we don't want to hit obscure cases very often. So if you want to hit if you want traces to be as independent as possible, and if you use prime numbers, that gets as independent as you get. And then you compile to assembler, and as I said, x86, as Alex said, x86 and x86 64 is the only supported platform as far as the release goes. But there's ARM branch and PowerPC branch, and they're getting in like PowerPC compiles PyPy and almost runs or something like this, and ARM pretty much runs PyPy, but it's still not on trunk. So maybe I should show the PyPy cake. So cake has layers. PyPy also has layers, lots of them. So they like first layer is your Python code. This is completely separate to the interpreter. Then you have an interpreter, and you can just run your Python code on the interpreter. But interpreter is written in RPython, which means that you can analyze it. Analyzing means that you create a flow graph of your interpreter that gets like high-level, low-level flow graphs, and then it's the tricky point. You go and make either C representation of the low-level flow graph or a thing that JIT can understand. So as I said before, JIT is a graph transformation from the graphs of interpreter. So the JIT is not written for the Python language. Our JIT doesn't know about Python at all. Our JIT only understands RPython and not even completely. And then it's written as a graph transformation operation, essentially. So you create code for the JIT or code for the C, but this means that all this stuff is generated from a single source file. So JIT is complete by design. As long as our interpreter is correct and our JIT has no bugs, JIT will be correct for the interpreter, which means it's also complete. Which means JavaScript has these problems that like they didn't implement some obscure case, and suddenly your JavaScript code just ran into a place where they don't JIT and say, ooh, no, we don't support exceptions. So it's not true for us because our JIT is complete. It will, if you have hot loops, they will always get compiled by assembler. So you won't get only one language description. As I've shown, we have pretty decent tools. Well, they're debatably decent because sometimes you can't guess what's going on, but they're the state of the art at least. Well, that's true. So maybe a word of warning, like cases where we won't speed up stuff at all by JITting is cases where you spend significant amount of time in runtime. So those are examples where like long addition or set intersection where in CPython, the entire thing is written in C. It's not even true for set intersection because you need to compare Python objects. But for list.sort, also you have to like call back to Python. But at least long plus long never calls any Python code back. So the loop written in C will be hopefully as efficient as possible, and it's kind of impossible for our JIT to outperform that. So we'll just leave this to runtime. So those are cases where people get constantly confused. Oh, but my PyPy code doesn't run faster than CPython. Yes, because well, you spend most of the time in runtime. There's not much we can do with the JIT, at least. We can optimize it other ways, but that we are not in any more lag than CPython in this regard. So well, to sum up, like JIT never considers operation in isolation. They always come in chunks. JIT always works on like a loop or a function at one time, and optimizes what we believe is common Python. That might differ from other people's beliefs, but it's important to note that what we believe is simple Python will be optimized. It's often much faster than CPython for things that run at least 1 second, for example. Depends on the size of your program a bit, but typically if your program runs 0.1 second, there's no point in trying to even invoke PyPy, because it will not get the time for JIT to warm up. So heuristics, we specialize on some stuff and not specialize on other stuff, and the good example of heuristic is ticks versus objects. So we assume ticks have a large set of independent keys that can change at any time, and it's not uncommon for a tick to have a key that's stored and read once, for example. While objects would be, you can treat object as a dict in Python. You can just do set utter and get utter, and I've seen people doing that at least. So objects, in our opinion, will have a constant set of, a small set of mostly constant keys. Doesn't mean we enforce this, but it means it will be faster if you do this. So an example, up, no. What's going on? So you have an object, and then a good usage of object would be to use objects like access attributes, and then all the time attributes accesses are constant. It's important to know that PyPy doesn't quite care if you write this or you write that. Well, it cares if you write backslash here. So this is the same code essentially. I mean, this will probably contain a check that you didn't override get utter in your built-ins by chance. But other than that, the code stays the same. If you, however, do like something like plus I here, then it's entirely different story. So this is a bad usage of an object. PyPy doesn't like that. This is a relatively bad usage of a dict, not in the sense that it will be slow, but in the sense that you can write the same thing much faster using an object. And this is like a typical usage of a dict. So if you run it, I don't understand how this quite works. Oop. 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 So we go there. By the way, the extra doc repo is here, and you can, ID, what's that? It's on bitbucket.org/pypy/extradoc, and you can find all the examples and the slides there. If you want, you can just go and poke at it. Anyway, I'm now on PyPy in the virtual end. I will run the 05. Yes. Examples 05. Thank you. So few things in object contain take like about 0.3 seconds, and a lot of them will take 10 seconds, for example. So, well, if I run it for too long, my computer will shut down from overheating. So the dict, for example, many in the dict is slightly faster than many in the object, but the thing is the difference between using few in a dict and using few in an object. So if you have a constant set of, this is just an example of a heuristic, but if you have a constant small set or mostly constant set of small constant keys, you should use an object and not a dict, even if you don't know them in advance. So another thing is specialized lists. So PyPy will, yes? Yes, slots are completely pointless on PyPy. They don't save anything. There's a number somewhere. No, I think it's like 25 or something.
It's not necessarily with the number so much as it is whether it's a constant set of them.
Yeah, it is a bit. If you have a constant set of 1,000, that wouldn't work quite nicely. It's like you'll probably see like a sliding scale, so it won't have a threshold, but it will get slower and slower as you add more from like some number, like 20 or 50 or something. I don't know, measure. If you have 50 attributes in your object, you have other problems, I think. So another example is specialized lists. So specialized lists are, if you keep only ints or floats in the list, it will store them unpacked, not with boxes. So that's very fast. For example, list.sort on a list of ints doesn't have to call any Python functions or look up anything. It just sorts them as fast as C. And range is a special kind of list. So if you, for example, append a non to int only list, you'll have to rewrite the entire list with like objects, and that's quite expensive. So it's another example of a heuristic that's actually very helpful in most cases, but sometimes it's in your way. So, well, I have some examples, and generally simple is good, and Python is a very large language. So if you use pieces that we never seen before, chances are they will be slow. I have a very good example where we just wrote a random stuff. How does this even work? Maybe like this. No? Yes. So I have a usage of ether tools. I'm sure there are people who would disagree with me, which is the simplest, but I claim 3 is the simplest from the JIT perspective. It's you take 2 vectors, and there are like several ways to write it down. And everybody will come with a different solution, but the thing is, we promise you that the third one will be among the fastest. JIT is complete by design, so it will JIT all of them, but every now and then there will be some obscure detail, and like one of those will be slow. So this is a very important thing. If you write simple code, it will run fast. If you write complex code, it might run fast, but you actually have to measure. So this example, and the thing is, we didn't quite know how this example will perform, and I just like randomly wrote few examples, and this comes with very surprising. So like the third is not quite the fastest, but it's definitely among the fastest, but it's like over 10 times faster than other ones. So it vastly depends on how you structure your program. And on CPython, they take like mostly the same time. So this is 2.7, and they all take like about like. So you get tons and tons of speedups if you actually write the simple stuff, and quite a bit of speedups if you don't. But there's definitely a difference how you write the code. Well, regular zip has to create a list, which relatively expensive. So the thing is, like, the simple stuff only iterates over a list and never actually allocates anything. It'll only add to the sum. So zip will not be fast, and izip can be made fast, but we just didn't. And yes, it probably requires like careful looking here and there and thinking what can be done. But the simple thing doesn't contain a single allocation, and that's the point mostly. So yes, the point cannot be stressed too much. Simpler is good for the JIT. So I have it twice. Things we could improve but didn't get to is frame access aborts JIT. And not that we cannot compile it, but because assembler suddenly gets huge. So right now, frame access just it works completely, so you can run PDB and everything, but it completely aborts the JITting.
So, for example, is like sys.execInfo is going to completely abort the JIT because it has to look for things in strange places, and the JIT does not care for that. Another example is like if you use the inspect module to go 2 stack frames up and read the request variable, JIT's going to abort again on that. This is an example of what we would consider not simple, not fast as a result.
Yes, so, well, either don't do that or bother us enough that we'll make it fast. Yes, I think it's really ugly, besides being obscurely slow. So there are other reasons for not using this. But yes, if you want to support Python from the same source from 2.5 to 3 point something, use sys.exinfo. And this is making JIT cry. So, well, I want you to have a look at the code and like try to run stuff. And essentially, assuming you have PyPy, get the JIT viewer from the, you need like PyPy and Python checkout, PyPy checkout and PyPy installed in the virtual env. So I use the virtual env tools for that, but feel free to use virtual env alone. And then install JIT viewer and then try to poke first at the examples. Like the JIT viewer comes with the log.pypy log or something, and you can poke at the examples, and there's source.py file that shows a few things. I will walk through them if you can get the JIT viewer to run. But we want generally to give you like a piece of code to optimize and then see how it goes. Like the piece of code is on the USB sticks under bench directory. So we suggest you take this piece of code and like try to look at it in JIT viewer, run the benchmark. We wrote the benchmark there. And essentially this is the exercise is that we took the JSON from before we did optimize it and after we optimized it and to compare performance essentially. So this is the standard library JSON module and it comes with like few problems. For example, the standard library JSON module has a C speedup and the way it's written, the C speedup crosscuts at a very weird API layer. So this actually makes pure Python version slower. So, well, how many people have JIT viewer running? None. Maybe we should first get JIT viewer running and then we can like walk through a few examples.
Does anyone need help getting it set up?
Yes, we will help you. We have like 5 people to help you with JP hiding there. Okay, so you need to set up your Python path to point to your PyPy checkout. I always have it, so I missed it. Oop. It's like, for Bash at least, it looks like this. Hop. So, stuff. You need PyPy checkout in your Python path. And then you go to JIT viewer, wherever you have it. JIT. And then you run JIT viewer log.pypy log. Hop. Boom, I have already one running.
well, you are in the virtual env.
Yes, well, if you did MK virtual env, you are in the virtual env.
Yes.
What's going on?
No, I cannot explain it because I don't know.
What?
So, I would like now to show the example of the JIT viewer when running this particular code. I mean, in the order of starting from the simplest one, this runs this function containing this completely trivial code.
It's source.py in the JIT viewer directory, so you can poke at it. We increase the numbers a bit here. Microphone. Yes, sorry. Okay.
Mm-hmm. Okay, so the way you look at this is well, it shows you every loop or every single function that was compiled by the JIT, and it's sorted in number of times that it was run. So it means if you have a real program and use this JIT viewer on it, well, the interesting points are the first few, of course. But well, I mean, in this example, we'll go here to F for the first example. Of course, it's very far down and it's completely uninteresting. But well, the point here is to show you how this function F was compiled. So you go. Oops. Ah.
You click the correct one.
Is it the correct one?
Yes.
Okay. Okay, so what this shows you is here you have the source code. So, I mean, it contains at least only the part of the function that was part of the loop that was compiled. So the while and the I plus equal 1. And then in these boxes you have aligned to the left in uppercase the bytecode. So it's really the bytecode in the standard Python way. I mean, it is the same bytecode that you would have in C Python mostly. And then indented you have the detail of the operations that the JIT thinks it needs to do the same. So these operations are mostly assembler instructions. They are assembler level. So it is an intermediate representation that then gets turned into assembler. And if you are really interested in actual assembler,
the box is out of the. You need to. The font has to be smaller. It's because I'm not a web developer. I don't know how to do it. Hop.
Yes. Can you? Yes.
Yes. Now
Okay.
we have the assembler.
Yes. So here you see, for example, that these two instructions actually correspond to these two assembler instructions only. So this is of course a completely boring example, but this example is incredibly fast because 1, 2, 3, 4, 5, maybe 6 or 7 assembler instructions run it for you. Okay. Can you hide it again, maybe?
Yes.
Thank you. Yes, the show assembler, the show assembler link does not work actually on OS X, sorry, because you need it use obj dump, which is not installed on the normal OS X. Okay, so I mean, if you want to look a bit more in the detail here, every variable starting with I means actually a register containing an integer. I mean, a register, or if there are actually more variables here than there are typically registers on the x86, then it's actually spilled on the stack and all these things. But well, you can really think about this as a register. So this means compare the register with this constant, you get a result, and this means well, guard that it is true means actually if it's false, jump somewhere else, where somewhere else contains codes to resume the situation. And here, well, here to do the I plus equal 1, you see, well, for example, these 2 byte codes, in the sense of Python, do not actually generate any low-level code, but only the in-place add will do the I plus 1. And this, well, yes, this example, well, in order to explain to you how we go from Python bytecode to this super optimized assembler, there are actually levels and levels and levels.
But I mean, we are at something like 7 instructions and C something like 5. Like it's not much slower.
Mm-hmm. I mean, you really have to think that this is actually doing something that on the Python level, well, on the Python level, it's actually manipulating objects, not real integers that goes into a C or an assembler register, of course. But all these object manipulation were completely removed here. And then here you have an addition plus 1. But maybe this can overflow. And then if it does overflow, then you would need a long, well, everything you usually do in Python. But no, in this case, it cannot overflow, because you add 1 to a variable that you already checked is smaller than 1000, so it cannot overflow, etc. It's really a combination of all these factors that give you this completely efficient code. Yes, and these 3 lines are checking for Control C, and this line, well,
you don't want to know.
This line actually, it's a so-called out-of-line guard. If you already saw the term used about some other JIT, it is a guard that compiles to no assembler at all. It's a guard that can fail, but if some other part of the interpreter would suddenly change a value so that this guard would fail, then it's a job of the other part of the interpreter to go and actually patch your assembler. So that's why it's actually no assembler code.
Next one.
Yes.
Yes. No, source is Python.
Yes, but yes. Well, here you really have to think that the source code is Python. It's a full Python.
Our Python is not in the equation, like it's a detail.
Yes, if you take this and say that it is actually R Python, well, yes, it turns out to be R Python, yes, and you compile it to C code, and then you get the same thing. But no, well, you don't get the same thing because you will not get automatically its Control C detection, and you will not get the overflow detection. The overflow, well, the overflow detection, which was actually removed in this case. But
Well, any more questions to that example?
yes, the point is that it is the assembler that you get is still implementing exactly the same semantic as the full Python semantics. Okay. The next example, it's mostly the same, but with a call. Sorry. Okay, so mostly the same, but here you have a call to a function, and here it returns the I+1. So
Inline call somewhere, inline
where is
string
it?
stuff.
Here? Yes.
Hop.
Okay. So it starts with the comparisons, the same as before. Then here you have a load global to load what is the name inner. So this becomes a guard not invalidated, which means no code at all, actually. So it means that if by any chance you have some random code somewhere else that changes what is this global, then things will still work, because at the point when this global is changed, it will patch this assembler to make it invalid. Okay, so what we have here, I mean, here it's just well, here you have the call function, and the called function is actually inlined in the source code, but that's only for displaying purposes. Here it's displayed as a link, and you have to click on the link. And here you see the execution as going on in the function. But you have to think about it as, well, this is inline in the caller. For example, manipulating the I-35, which really comes from the caller.
Also very efficient.
So yes, basically, this is, well, I mean, if we compare with what we had before, there is only this instruction in addition, and this actually turns into no assembler too. So yes, so in this case we completely removed any overhead from calling the function.
Okay, then a slightly worse example. This one.
Well,
This has
yes.
a breach and an uninlined call.
Okay. So this has two different things in addition to the previous example. You have this, which is a so-called uninline call, because it calls this function which contains itself a loop. So our tracing JIT, whose purpose is really to follow every instruction as it goes, here it will stop. I mean, it will actually inline the start of the call, but then when it reaches the loop, it will stop. So how does it look?
Outer or inner?
The outer first, please.
Breach. This one. Yes, you can see here that the modulo instruction in Python is actually completely not the modulo instruction in C. It's a different operation.
Yes, it's also a bit of a mess that we could maybe optimize a little bit better, but okay. I mean, the main issue is that doing an X modulo Y in Python that does not have the same semantics as in C with respect to negative numbers. So we have to correct. I mean, this is doing the assembler instruction modulo, but then we have to correct things, correct for sign issues.
Failing guard.
Yes. This is which case? Yes, this is the case where we take this path. So it's just represented as a guard that the result of the modulo is not true, so it means is 0. Okay, so I mean, in one case we just do that. Here you have an example of +1 that is actually an integer addition overflow, which means it becomes in the instruction addition of registers, but then it's followed by a guard that it did not overflow. Okay, but and then this is of course the first example that we are showing in which the control flow actually changes during the execution of the loops. So in this case, it shows this guard fails often enough, in the sense that you run this 10,000 times, and at 5,000 times the guard is going to fail. So when the guard starts to fail too often, what we do is compile a bridge, and a bridge is a name for the term that you have this as a loop, and the bridge is where you would like to jump to. It's another potential tail of the same loop.
Yes, I claim 0% is not every second go, but probably it's like integer division or something. Now it's worse.
Yes. Why? Yes, I know. Okay. Yes. So in this example, now it's worse. What we're doing is calling the load global on the call like before, but it really contains bits extra guards here. Where is the actual call? Yes, here.
Yes, it's inline call to uninlined call.
Okay, can you follow?
Up. Yes.
It contains the first iteration.
And then frame allocation, and then call assembler.
Yes,
yes, it's a good example where it's not great, and we are trying to improve it.
So what is occurring here is that the first iteration through the loop is actually inlined, but then the further iterations are not. So the first iteration becomes this, where you have the addition of 1. Yes, for example, s plus equal 1. Well, s, it's 0 anyway, so it's all constant folded. Okay, and here you have the call. I mean, when we the point is that the control flow here is really completely different than the control flow of your source program. Meaning every call that every call that occurred in your source program is inlined, always. But if a call goes to a function with a loop, then what will occur is that at the level of assembler, it will turn into a call to a function at the level of assembler that implements only the loop.
So who got confused? Well,
it does look less than optimal.
Yes. Well, explain maybe why.
Well, really?
No, it's kind of interesting. If you call another function on the assembler, you suddenly no longer inline your caller, which means you have to allocate the Python frame. We are working on removing that, but we didn't quite yet. So allocating Python frame means that you have to pass stuff in a shape that would come from the interpreter, which in this case means, for example, we allocate probably, this is frame allocation, then we allocate a place for locals, then we allocate like 2 locals and something, and then a list object that's probably another local, and then we have to like carefully stuff there. Like you can see here, we store the backref to like our frame. So this would require another level of optimizing the frame allocation. And then we store, for example, like all the stuff that the Python would do normally on the frame. So you initialize the frame essentially. And yes, this look obscurely inefficient, but remember that this is still much faster than if you would run it in the interpreter, because this would happen at every call, and we only do it like every few goes. And this is also, it's still optimized inside. So if we follow this, hop.
Yes, so now we are looking at the code of the loop that was in the non-inline function.
Are we going back out to the interpreter when we do that? Is it like
No. The call is really a call at the assembler level that really goes there directly.
So the funny thing is now we unpack the frame that we just created into local variables. So it's clearly optimizable.
Mm-hmm.
Yes, this just does that.
Mm-hmm.
Hop.
Well, can you, yes.
Yes, okay, so we have another unrolled iteration and hop.
Mm-hmm. Yes, and well, here you finally have the efficient version of this for loop. I mean, here it's a bit more instruction than what we have had seen previously, because it's a for in the, I mean, it works in the range object now. So for example, here we still have a multiplication with one of these that's probably always a constant 1, because that's a step in the range.
Yeah.
We didn't quite figure that out yet,
Mm-hmm.
but yes.
I mean, yes. From one point of view, just doing this kind of demo just shows some completely obvious inefficiencies. But then you also have to take the other point of view, which is that this is really assembler instruction. So yes, we can remove one assembler instruction, but the total of 10 assembler instruction is already incredibly much faster than CPython.
Well, the bridge, loop exit bridge.
Mm-hmm. Yes, so this is the guard that will fail when the range is exhausted. And what are we doing here?
Storing stuff back on the frame.
Yes, we are storing again everything on the frame, on the frame that we're about to leave. That's just because, just in case someone actually got a reference to the frame at the Python level, stored it somewhere, and much later would ask, what was the value of this local? Well, it's supported.
I guess this exhausts the example, really. Then we go back to the caller.
Mm-hmm. Yes, and yes. So all these, well, everything that we have shown is really assembler that calls other assembler. There is no path where we give up and call back the interpreter.
And as you can see, there's still place to optimize. Like, we are by far not done. It's like you look at those traces like, oh my god, this is obviously optimizable. Like, we should do something about that.
But this is a case where, although it looks horrible, this is an example that is not real. I mean, you wouldn't actually
Yes,
create a
that's
function
true.
that does s plus 1 3 times and then returns.
You sometimes do. But
Well, yes, I mean, you have to. Well, yes, you sometimes do, also in the sense that maybe this is not an actual call to a function, but to a method of an object, and then it depends on what the type of object is. But for most of the case, the method you're calling is a one-liner. So actually, inlining it is an excellent idea.
yes, I mean, PyPy has very strange performance profile. Like, in this particular case, you'd see that there are pieces that are about 100 times faster than the interpreter, and the pieces that are only like 5 times faster. It's still much faster here, but the performance varies quite a lot depending on what you do. And yes, we are trying to widen it, but it doesn't always work. As of now. So, well, what do we explain? The obscure inlining of regular expression?
Well, yes. I mean, maybe I would just explain it by waving my hand here. It's that here you actually have a call to a a call to the regular expression module, and the regular expression is itself some kind of bytecode interpreter. It interprets the bytecode made out of the regular expression. So if it's a bytecode interpreter, we can apply the JIT. So we did. And so this regular expression call is turned into, well, assembler.
You bring up the trace.
Yes. Inline string stuff, one of those.
Not this one?
This one, yes.
Yes. So this is actually how a regular expression bytecode is compiled, as opposed to a Python bytecode. Which yeah, yes. I mean, it looks very similar. It's just the same mechanisms that we use. Here you have getting out of this string this character, checking that it is 51. What is 51? The character 3, maybe. Then there is a guard, and if not, you increment a variable that is the index, and probably, yes, just finish, which just means, well, look at the next character, simply. And that's a bridge. Well, doing stuff.
And finishing as well.
Yes.
Okay.
But yes, the point is that, again, this regular expression is compiled into these few assembler instructions.
Well, the interesting point is usually not to like try to understand exact assembler instruction, but to like guess the overall density, how much assembler and how much allocations I actually need to execute that. So, like in these cases, there are like 2-3 assembler instructions here and there are not really that interesting. Like removing one wouldn't give you much, but every now and then you will find yourself like, oh, this allocates frame and like populates with stuff, and that's like hundreds of assembler instructions, including the stuff in the GC, and that's much more interesting. This is the caller. No, this is the list comprehension.
Yes, which is a loop also, of course.
Yeah, of course. So this is maybe interesting.
Yes. It's a call to the function that converts the int to a string.
Assembler level int.
Yes. I mean, it's a call. I mean, here at the assembler level, it's going to be a call to a function that was compiled in C.
And this is the thing that resizes the list.
Yes.
Potentially. Up. Yes. This is the inline string, so for each element. And then yes, we inline the call to stuff in the regular expression.
Mm-hmm. Can you follow?
We compile.
Mm-hmm. Yes, well, yes. I mean, here we are in the module re.py.
Like hash a tuple.
All the dictionary calls here, do you have a dictionary object that you call into? Or are you splicing code in line? Or?
Yeah, no. All things about dictionaries are really calls because it's too much.
Almost all.
Almost.
So yes, this is the dict lookup. For example, this is the actual dictionary. It's not an object. An object would not have this. An object would have the dict lookup at the moment you compile the assembler. This has dict lookup dynamically because you don't potentially know. Yes, dict lookups in Python can execute arbitrary Python, including one that modifies your dictionary by calling comparison of a strange object. Hop, 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 hop. That's it.
Where is the call?
It's a night function. So,
Okay.
so you go up.
Well, yes. Well, yes. I mean,
And are sets
what
something that you call back to the regular Python implementation? Sets, set objects?
no, they are like dictionaries really. Dictionaries who don't have a key.
A value.
Yes, sorry.
So yes, this is interesting. So you compiled your regular expression here, and that took a beat, and then you call method search on it, which does quite a bit stuff. It prepares the pattern somehow and like reads some items. This is reading some code. Not sure what's that.
That's probably the startup code.
Yes, and then you inline the call here, which is then again the call in the assembler, in the assembler that goes to the regular expression engine. So you just have one JIT calling another JIT, and it's completely inline. You don't have going through the interpreter at all. And it calls more stuff. And we are back to the place where we've been. I think the only other unusual pattern that's really obscure is that double loop stuff. So this is another example where the assembler representation is completely detached from what you write in Python.
Yes. What occurs?
Hop, should I just show it?
Yes. Okay. So what occurs is you see here the inner loop first, just because it's the one that is run most often. So it first compiles the inner loop, and well, this looks like what we have seen so far. Okay. But then what would occur when this iterator is exhausted? It would go there, follow this bridge. And if we look, this bridge, well, has pop block, which means end of the for loop. Does a bit of thing.
Jump absolute.
Jump absolute, which means jump to the start. So really here it's doing the outer loop. The for iter, which will fish the next item out of the range, and we see here, as usual, our multiplication by 1.
Yes, then we create another range,
Yes, true.
the inner range,
Mm-hmm.
and that's it.
Mm-hmm. Well, it's all some number of instruction, but you still have to think that everyone becomes 1 or 2 assembler instruction only.
Hop.
And
You put stuff back on the frame and jump back. The crucial part is that you have inner loop, which is small, and outer loop, which is inlined as a bridge to inner loop. So you have like reversed flow, because this is the way stuff gets hot in running of your program. No. So I guess roughly
yes, I mean, here we have shown a bit small, well, completely trivially small examples. But the point is that this tool, the JIT viewer, is actually useful if you try it on large example too. Because well, what you will see is the first few entries that are the most executed are the one. Well, that's why it's interesting to go, and then it's interesting to find this kind of code, which means tons and tons of instructions that corresponds to no or to just a few Python byte code. So in this way you can find out where the optimization was not so successful, basically. Yes.
Well, you can either do it yourself or get back to us. Like,
Mm-hmm.
but yes, essentially, I think the plan for now is like you guys all feel free. I don't know. It's about another hour or so. What time is it supposed to end?
4:48.
Yes, so hour and something, and we can have a little break, and then you guys, there's a benchmark on the USB stick, the JSON benchmark. You guys are free to run that or any other of your stuff, and we'll go and help you and explain what's going on. So The original idea, I think, was to take the JSON benchmark, try to optimize it. I'm not sure we have enough time, but at least we can look at the JIT traces and see what's going on and where the stuff is going. So the JSON is the actual JSON from standard library Python 2.7, unmodified, which means also with tons of stuff that's not completely necessary in PyPy, like if something has C speed up, which we don't. So it's maybe interesting to look how real code looks in JIT viewer, but also feel free to run it on any of your code and like ask us for questions. I guess that's the plan.
Essentially, you run PyPy, point it at your source program, and then you add this extra environmental variable, PyPy log equals jit-log-opt, comma, jit-backend, log.pypy log. And basically what, sorry?
File name.
Yes. So essentially what that's saying is we would like the log to contain the optimized logs of all the instructions we've been looking at, backend, which contains the number of times each loop was executed, and then it dumps it to the log.pypy log file. And so that's the name of the file you'll then point JIT viewer at to display it. Yes, so we'll leave this up. Yes, and the JIT viewer README has that thing as well. So. Sorry? Oh. Okay, so we are now here to answer any and all of your questions.